Hello, Intro to Material Science class. My name is Francine Salvador, and I'm going to be presenting about the face-centered cubic structure for my final project. The topics I'll discuss in this presentation are the face-centered cubic structure in the 3D space, how to solve a theoretical density problem given the crystal geometry, and I'll also touch on understanding crystallographic planes and Miller indices. So we can start by discussing what crystal structures are. What we typically see in metals, in many ceramics, and some polymers is dense, periodic, ordered packing at the atomic level. Metallic crystal structures have the simplest ones, which include the simple cubic structure, the body-centered cubic structure, and the face-centered cubic structure. So I have a photo of a Tinkercad model I made of an FCC, and I will get into the 3D workspace in the next slide, but I did want to show you the 8 corner atoms that are in red and the 6 face center atoms, which are in white. They're all identical atoms, but they are color-coded for your viewing pleasure. One thing about the face-centered cubic structure is that it has a coordination number of 12, which is just the number of neighboring atoms. And I can show you that in the next slide when I get into Tinkercad, because it's a little bit easier to visualize in the 3D workspace. The face-centered cubic structure also has an atomic packing factor of 0.74, which is just basically how much space the atoms are taking up. It's the volume of atoms in the unit cell divided by the volume of the unit cell. And I have the formula for that at the bottom listed. And the 4 in the numerator is indicative of how many atoms are in the unit cell, which is going to be 4. And I can show you that as well in the 3D space. So let me move over to Tinkercad and I will show you what I'm talking about. So here's my 3D model. Basically the same as what I showed you in the photo, but one way to visualize the coordination number is if you focus on this atom right here and imagine the same structure stacked on top of this one. You'll see the 4 corner atoms are neighboring atoms, the 4 face-centered atoms on the plane below are neighboring atoms, and then this same structure is going to be up here on the plane above. So we'll see 4 times 3, which will be 12 for the coordination number. And that kind of helps you to visualize the stacking sequence of the FCC as well. And another thing that is fun to visualize in the 3D space is how many numbers of atoms are in the unit cell. So if you kind of imagine these bonding stick, imaginary stick things splitting the unit cell, you'll see that each face-centered atom is split into half and each corner atom is split into fourths. So if we multiply the 6 face-centered atoms by 1/2, it would be 3 atoms and a quarter of each corner atom, which will add another one. So 4 atoms in the unit cell. And that's all I really wanted to discuss in the 3D portion of the presentation. So I'll go back, and now that we know a little bit more about the FCC, we can talk about solving a theoretical density problem. So the way a material is structured at the atomic level can help you predict some properties about it, including its density. So that will just be the mass of atoms in the unit cell divided by the volume of the unit cell. And we saw some of these terms in the APF formula in a couple slides ago. So I have an example problem here at the bottom for aluminum, which is an FCC structured material, and it has an atomic radius of 0.143 nanometers. So given the atomic radius, atomic weight, and the crystal geometry of the material, we can calculate the density just by using this formula listed right here. And here I have it as 2.71 grams per centimeter cubed, which is only 0.01 off of its actual density to 2.700 grams per centimeter cubed. So then you can also do this backwards if you're given, for example, the density and you wanted to find the radius. Just given that kind of information, you can do the same process in reverse, just knowing its atomic radius, atomic weight, and crystal geometry. Another topic I wanted to touch on was the crystallographic planes and Miller indices. It's a pretty simple process to be able to read a plane in its Miller indices. And that's just to find where a plane intercepts with the axes, take the reciprocal of these intercepts, and then multiply it to make the smallest integer value. So I have two examples here. One of them is a plane that I put onto my Tinkercad model. You can see it's in a transparent pink color, and another one I just drew myself. And they're both pretty simple and easy to read. So we can see on the left here that the plane intercepts with the unit cell at 1 for x and y, and infinitely in the z direction. So when we take the reciprocal of these, it will be 1 for x, 1 for y, and 0 for z. So its Miller indices are 1, 1, 0. It's the same process for the example on the right that I drew by hand, so I'm sorry about that. But in the x direction, the plane is going infinitely. In the y direction, it intercepts at 1, and in the z direction, it intercepts at 1/3. So when we take the reciprocal, it will be 0 for x, 1 for y, and 3 for z. And this will kind of just help you to read the plane with Miller indices and draw your own planes, which is a very helpful skill. So I hope that my presentation has helped you to understand a little bit more about FCC, about theoretical density, and about the crystallographic planes. Thank you.